So on the problem number 22, we have the function f of x equal x squared plus 2x minus 15 divided by x squared minus 2x minus 3. The first thing we want to focus on is on the denominator. My x squared minus 2x minus 3 cannot be equal to 0. If I want to find the value of x that makes this denominator equal to 0, I need to solve my quadratic equation x squared plus negative 2x plus negative 3 equals 0. Why do I put the plus? Because remember, the general expression of a quadratic equation is ax squared plus bx plus c. By adding the plus, it doesn't change anything. Plus multiplied by minus give you minus, so it's not a problem. But at least it helps you to figure out that a equal 1, b equal negative 2, and c equal negative 3. It does help you to avoid to make a mistake, because when you make a mistake on a, b, and c, you will have your 0, the value of your vertical asymptote or the 0 of your quadratic equation would be wrong. So when I calculate these two zeros, I end up to have two values, 3 and negative 2. Take your time. When you manipulate negative numbers, don't forget to put them into parentheses. And so I have two vertical asymptotes, x equals 3 and x equals negative 2. If I want to look for the horizontal asymptote, I am going to divide by the greatest degree of the variable with the greatest degree of the variable with the greatest degree in the expression. In that case, for instance, it is x squared, and so I am going to divide by x squared. Let me use another color. I'm going to divide by x squared right here. I'm going to divide by x squared and divide by x squared, and I will do the same thing below. So I end up to have what at the end? I end up to have a function f of x equal, so let me have access to the problem again. It's equal to 1 plus 2 over x minus 15 over x squared over 1 plus 2 over negative 2 over x. It's not a plus, it's negative, so minus 2 over x minus 3 over x squared. And when I look at 2x squared, 2 over x, 15 over x squared, but also 3 over x squared, when x goes toward infinity, the absolute value of x goes toward infinity, this value are getting close to 0. So therefore, my function f of x, it's basically 1 plus 0 minus 0 over 1 minus 0 minus 0. So I end up to have f of x equal 1. And so y equal 1 will be my horizontal asymptote. All right, so now what problem do we have to do? So on this problem number 29, if you look at x equal 2, you will see that you have a vertical asymptote. And if you look at y equal 4, you will have an horizontal asymptote. Now, when you go from the left to the right, you end up to, and why am I going from the left to the right? Because I want to define the domain. I'm going to have negative infinity, and then I'm going to reach the vertical asymptote x equal 2. And because it's an asymptote, 2 is not part of the set of solutions, union 2 to plus infinity. Number 35. All right, so what do we have in this problem number 35? It's the same idea. I'm going to do it right here to save some space, even though I have plenty of space, right? I can see that I have a vertical asymptote, and this vertical asymptote is at x equal negative 1. I got this vertical asymptote, but I have also an oblique asymptote, and this oblique asymptote is defined by y equal x minus 1. Y equal x minus 1 is the oblique asymptote. How do I define that y x equal x minus 1 is the oblique asymptote? I can just look at some of the point of intersection that I have. Clearly, when I look at my y-intercept, I got 0, negative 1. And when I look at my x-intercept, I got 1, 0. So again, your y-intercept would be 0, negative 1, but your x-intercept would be 1, 0. Problem number, and I need to look at the problem number. In this problem 37, we do not have vertical asymptote. So vertical asymptote there is known, but there is an horizontal asymptote, and this horizontal asymptote is y equal 0. When I look at the domain goes from negative infinity to plus infinity. Number 39. Number 39, sketch a graph of each rational function. So I got a function f of x equal x plus 1 over x minus 4. So the first thing I want to do is do the division, x minus 4 dividing x minus 1. And I'm going to have 1 by x give me x, 1 times negative 4 give me negative 4. Because I'm doing the long division, I'm going to subtract, and I end up to have this negative 4 become plus 4, I end up to have plus 3. So this function f of x, x plus 1 over x minus 4, is going to be equal to 1 plus 3 over x minus 4. So if I start from, if I want to graph that sketch, the first thing I want to do is notice that I have a function h of x minus 4 that can come from the function g of x equal 1 over x. And so obviously this function h of x minus 4 corresponds to a shift to the right of 4 units of the function g of x. So if I have to graph my function g of x, and 1 over x is something like this, and we know that there is a vertical asymptote at x equals 0, there is a vertical asymptote, but I know also there is an horizontal asymptote at y equals 0 for g of x. Because I have a shift of 4 units to the right, I end up to have basically a vertical asymptote that is going to be x equals 4. If I just think in terms of shifting to the right, my vertical asymptote x equals 0 is also going to move to the 4. So 1, 2, 3, 4, I am going to end up to have a x equals 4. X equals 4 will be a vertical asymptote of h of x minus 4. And so if I graph g h of x, x minus 4 equal 1 over x minus 4, I know that I will have also the same horizontal asymptote, y equals 0, and so my function will be like this. But what I'm looking at is a function f of x, and we're having the plus 1. The plus 1 indicate that my function, so I have 3 times 1 over x minus 4. This 3 right here correspond to a stretch, vertical stretch of my function h of x minus 4. The vertical stretch is not going to change much rather than just being something more like that. I stretch all the value, and that will be 3 over x minus 4. But then I need to consider the fact that I have plus 1, and this plus 1 right here corresponds to a shift up of my function 3 over x minus 4. And I know also that means that I have an horizontal asymptote at y equal 1. So in fact what happened is when I shift up of 1 unit, I basically end up to have my horizontal asymptote y equals 0 moving up of 1 unit. And so basically what I have, if I want to respect and keeping my, so I got right here, I'm going to do that right there. If I have this like that, and I'm going to keep my initial y equals 0 being here, and I know that right there I had at the beginning x equals 0 was right there for my vertical asymptote. This is the x-axis also, and this is the y-axis also. I know now that I have a shift up of my function, And so mainly what I have is something like that. All right, guys. So let me do one more problem, I think, and then we will be done. All right, guys. So what we need to do is very simple. If I want to graph that function, I am going to FOIL my numerator, and I'm going to express x minus 1 square. I end up to have at the end x squared minus 2x minus 3 equal x squared minus 2x plus 1. If I want to find the horizontal asymptote, I'm going to divide by the variable with the greatest degree, which is x squared. And I end up to have at the end, following the same methodology than before. Please watch the video attentively, part 1 and part 2. This is being the part 2. And we end up to have 1 minus 0 over 1 minus 0 plus 0, because 1 over x squared is going towards 0 when x is going toward infinity value. And so we end up to say that y equal 1 is the horizontal asymptote. So I know that y equal 1, I have an horizontal asymptote. Then finally, I have x minus 1 square cannot be equal to 0. I want to focus on my denominator and study if my denominator can give me my vertical asymptote. And I can see clearly that x minus 1 cannot be equal to 0, so x cannot be equal to 1. If x cannot be equal to 1, that implies that x equal 1 is a vertical asymptote. So if I have to graph that function, I know that I will end up to have at x equal 1 a vertical asymptote. So let me do this right here. So x equal 1, I got a vertical asymptote. So I'm going to, here we go, x equal 1. This is x equal 1, my vertical asymptote. But I know also that y equal 1 is a horizontal asymptote. So I'm going to graph y equal 1 as my horizontal asymptote. And if I look at my what's my calculator is giving me, let me graph for you the function x equal 1. And we have the vertical asymptote. And if I graph for the other function y equal 1, I got my horizontal asymptote. So the calculator is also a good way to check what you are expecting to have in terms of asymptote and graph. All right, guys, thank you very much. This part 2 is done, and I will try to do the section 5.3 now.